Our universe is not a random scatter of stars. It is a single, organized structure of staggering scale, a cosmic web connecting all galaxies across the emptiness of space. Understanding this architecture is like discovering the master blueprint for reality itself. By the end of this journey, you will see how scientists map this invisible network and what it reveals about our cosmic origins and ultimate fate. How did the smooth infant universe evolve into this intricate web of filaments and voids? What mysterious, dark scaffolding holds the entire luminous structure together? What does it feel like to grasp a map that stretches across billions of light years? This grand architecture is known as the cosmic web. Picture the most delicate, intricate spiderweb you can imagine, but one spun across the entire observable universe. The glittering jewels of galaxies are not scattered at random. They are strung along its invisible threads, clustered at the intersections where filaments meet. This is the fundamental large-scale structure of everything, a scaffolding built primarily from the mysterious substance we call dark matter, with the galaxies we see merely tracing its outline like lights on a highway map. The discovery of this web was a profound shift in human thought. For much of history, we pictured the cosmos as a roughly smooth, even distribution of stars. Now we know it is a tapestry of immense voids and intricate structure, a universe that is fundamentally clumpy and connected. As astrophysicist J. Richard Gott III described it, the universe is like a sponge, a complex network of voids and structures. To understand this web, we need to look at its three primary components. First, the cosmic voids, unimaginably vast regions of near emptiness that can span hundreds of millions of light years. Then the dense galaxy clusters, the bustling metropolitan hubs where thousands of galaxies swarm together. And finally, the filaments themselves, the long, thin bridges of dark matter and gas that connect everything, the superhighways along which galaxies travel and gather. This entire architecture, from the tiniest thread to the largest void, began as microscopic quantum ripples in the fabric of space-time in the first instant after the Big Bang. Over 13.8 billion years, the relentless pull of gravity amplified those tiny imperfections, sculpting the smooth primordial soup into the magnificent, structured web we see today. To grasp the sheer scale, consider that a single one of these cosmic filaments can stretch for a length that would take light, the fastest thing in the universe, hundreds of millions of years to travel. This realization changes everything. It tells us our universe is not chaotic, it is deeply, profoundly organized, and that organization holds the key to our past and our future, setting the stage for an epic quest to map the unmapped. The first true glimpse of this cosmic web came not from a grand theory, but from a patient point-by-point mapping of the night sky. In the 1980s, astronomers Margaret Geller and John Huckrow were conducting a systematic survey, cataloging the positions and redshifts of thousands of galaxies. Redshift is the key, a cosmic fingerprint. As a galaxy moves away from us, its light stretches toward the red end of the spectrum. By measuring this shift, scientists can calculate not just how fast a galaxy is receding, but also its distance from us. It is the fundamental tool for building a three-dimensional map of the universe. What Geller and Huckrow found as they plotted galaxy after galaxy was not a smooth, featureless scatter. Instead, they saw a pattern emerging, a startling architecture. Galaxies were clustering along vast, curved sheets, like the foam on an ocean wave, separated by immense, dark gulfs of nothingness. Their map revealed a structure so colossal it was immediately dubbed the CF, a two-great wall, a filament of galaxies stretching over 500 million light-years across. It was a discovery that fundamentally rewrote our cosmic address. We did not live in a random suburb of stars. we resided on the slope of a mountain range of universal proportions. This was soon followed by an even more staggering find, the Sloan Great Wall, uncovered by the Sloan Digital Sky Survey in the early 2000s. This structure is a cosmic continent, a network of filaments over 1.3 billion light-years in length. To put that into perspective, if you could travel at the speed of light, it would take you over 1 billion years just to go from one end to the other. Our entire Milky Way galaxy would be a mere speck on this immeasurable tapestry, but the walls were only half the story. Between these glittering structures, the maps revealed profound emptiness. Regions like the Borealis void, a spherical volume of space about 330 million light-years wide containing only a handful of galaxies. If our galaxy were placed at the center of such a void, our night sky would be almost utterly black, with no nearby galaxies visible to the naked eye. These discoveries shattered the long-held cosmological principle, the idea that on the largest scales, the universe is smooth and homogeneous. The cosmos was not a uniform soup. It was lumpy, structured, and full of dramatic contrasts between dazzling density and profound emptiness. Each new survey added more points to the map, each redshift measurement a single pin in a growing model of reality. And as the pins accumulated, the outline of the web began to emerge, not as a theory, but as an observed, undeniable fact written in the light of countless galaxies. This era of cosmic cartography taught us a humbling lesson. The universe is always grander and more surprising than our best imaginations, pushing us to develop ever more powerful tools to see the bigger picture it was revealing. Galaxies are not the foundation of the cosmic web, they are merely its decoration. To trace the true architecture of the universe, we must learn to see the invisible. The glittering walls and clusters we have mapped are just the illuminated outlines of a far more massive, hidden structure, one built from a substance that has never been directly seen. This is the realm of dark matter. It is the universe's greatest open secret, comprising roughly 85% of all matter, yet it reveals itself only through its ghostly gravitational influence. Without it, the cosmos as we know it could not exist. The delicate filaments of the web, the immense gravitational wells of galaxy clusters, none of it would hold together under the gentle pull of visible stars and gas alone. The galaxies we see are like leaves scattered across the surface of a deep, dark river, their motion dictated by powerful, unseen currents flowing beneath. The first compelling clues to this dark reality came not from the vast distances between galaxies, but from their internal dynamics. Astronomer Vera Rubin's meticulous studies of how stars orbit within spiral galaxies revealed something perplexing. The stars at the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity and the amount of visible matter we could see, those outer stars should have been drifting slowly, like planets in the far reaches of our solar system. Their high speeds meant only one thing: there was far more mass holding those galaxies together than our telescopes could account for. This missing mass, this dark matter, had to be there, exerting a gravitational pull from the shadows. But how do you map something that emits no light? The key lies in a cosmic illusion created by gravity itself, a phenomenon called gravitational lensing. Albert Einstein's theory of general relativity tells us that mass warps the fabric of space-time. A massive object, like a cluster of galaxies dominated by dark matter, acts like a lens, bending the path of light from more distant objects behind it. When astronomers look at such a cluster, they often see stretched, distorted, or even multiple images of galaxies far in the background. By carefully studying these distortions, scientists can work backwards to calculate the total mass of the foreground cluster, including all the dark matter we cannot see. It is like mapping the shape of a submerged mountain by watching how it bends the waves on the ocean's surface. Through gravitational lensing, we can literally see the dark matter skeleton by observing how it bends the light of the universe. This invisible framework did not simply appear, it evolved. To understand its formation, scientists turned to immense supercomputer simulations. One of the most famous, the Millennium Run, starts with a nearly smooth, early universe seeded with tiny fluctuations. It then applies the known laws of physics, primarily gravity, and lets trillions of particles of dark matter evolve over billions of simulated years. The result is breathtaking. A cosmic web emerges in perfect detail. Dark matter first collapses into a vast network of filaments. At the intersections of these filaments, where the gravitational pull is strongest, dense knots known as dark matter halos form. It is within these halos that ordinary gas can collect, cool, and eventually ignite into stars, giving birth to the galaxies we observe. The simulations show us that the luminous universe is a direct consequence of this underlying dark architecture. Galaxies are born where the dark matter web is most dense. So when we look at a map of the cosmic web traced by galaxies, we are seeing only a faint echo of a deeper truth. The bright knots and threads are just where ordinary matter, the stuff of stars and planets, has managed to pool within the immense, invisible gravitational wells sculpted by dark matter. To truly understand the universe's largest structures, we must learn to read this dual map, the visible and the invisible. Knowing that the most profound features are written in a script of gravity, we are only just beginning to decipher. This realization shifts our quest from simply charting galaxies to weighing the void itself, a task that requires peering into the deepest shadows of space. But mapping the galaxy clusters themselves was only the beginning of the true challenge. To chart the entire cosmic web, we needed a way to see the invisible filaments connecting them, the dark threads stretching across the void. How do you map something that emits no light, that reveals itself only by its gravitational grip on the emptiness around it? The answer lies in one of the universe's most elegant illusions, a phenomenon that turns the cosmos itself into a giant lens. According to Einstein's theory of general relativity, mass warps the very fabric of space and time. A massive object like a cluster of galaxies laden with dark matter does not just sit in space, it bends space around itself. Think of placing a heavy bowling ball in the center of a taut rubber sheet. The sheet curves downward. Now, if you roll a marble past the bowling ball, its path will curve, following the dip in the sheet. Light behaves in exactly the same way. When light from a distant background galaxy travels through the universe and passes near a massive foreground cluster, its path is bent by this curvature. From our viewpoint, that background galaxy appears distorted, stretched into a faint arc, or sometimes even multiplied into several ghostly images around the cluster. This is gravitational lensing, a cosmic mirage that reveals hidden mass. It is as if we are looking at a distant street lamp through the bottom of a beautifully crafted but warped wine glass. We cannot see the glass itself, but by studying how it twists and magnifies the light of the lamp, we can deduce its precise shape and thickness. Astronomers do precisely this on a universal scale. By meticulously measuring the subtle distortions of millions of faint background galaxies, they can work backwards to calculate the total mass of the foreground cluster causing the distortion, including every ounce of its invisible dark matter. This technique, called weak gravitational lensing, is the most powerful tool we have for directly tracing the dark matter web. Projects like the Dark Energy Survey do not look at just one cluster. They scan enormous swaths of the sky, cataloging the shapes of hundreds of millions of galaxies. Where they find a consistent statistical pattern of stretching, a coherent warping of spacetime across a vast area, they know they have found a dark matter filament. It is a painstaking process, like listening for a single, consistent note in a cosmic symphony of noise, but it works. Through lensing, we do not just infer the web exists, we can begin to draw its outline with observational ink, confirming the grand architecture predicted by supercomputer simulations. This allows us to weigh cosmic voids as well, measuring how much their apparent emptiness still subtly bends the light passing through, telling us just how truly empty they are. With this technique, the dark matter skeleton of the universe slowly comes into focus, not as a theoretical sketch, but as a measured gravitational reality. It proves the filaments are real, massive, and form the foundational grid upon which the luminous universe is built. Yet, even this profound method has its limits, relying on the chance alignment of distant galaxies. To create a complete three-dimensional census of the cosmic web, we needed a method that could see the structure itself, not just its shadow. This required turning our gaze to the faint, ancient glow that fills all of space, a fossil light from the dawn of time. The faint afterglow of the Big Bang holds the original blueprint for the cosmic web. This ancient light, known as the cosmic microwave background, is a snapshot of the universe when it was just 380,000 years old, a time before the first stars or galaxies had even formed. If you could see this glow with your eyes, it would look like a nearly uniform, warm haze filling the entire sky. But to our most sensitive instruments, it is not perfectly smooth. It is mottled with incredibly subtle temperature variations, tiny hotspots and cold spots differing by mere millionths of a degree. These imperfections are not random noise, they are the cosmic seeds from which the entire web would grow. They are the frozen imprint of the universe's most dramatic infancy, a period of unimaginable expansion called cosmic inflation. In the first fraction of a second after the Big Bang, the universe is thought to have undergone a growth spurt of staggering proportions, inflating from a subatomic speck to something vastly larger in an instant. During this hyper-expansion, the very fabric of spacetime was a seething quantum foam. Microscopic fluctuations, tiny ripples in energy and density, were inevitable at this scale. As inflation stretched the universe exponentially, it also stretched these quantum ripples, magnifying them from the quantum realm to cosmic proportions. Imagine blowing up a balloon that has a fine, barely visible texture painted on it. As the balloon inflates to an enormous size, that subtle texture expands into a clear, continent-scale pattern. Inflation did exactly that to the infant universe, turning quantum fuzz into the first large-scale wrinkles in reality. Those wrinkles in density became the gravitational starting points for everything to come. Slightly denser regions had a tiny bit more gravitational pull. As the universe continued to expand and cool over the next few 100 million years, gravity acted like a cosmic amplifier, relentlessly pulling matter toward these overdense spots. Ordinary matter, in the form of hydrogen and helium gas, began to flow along the contours of this invisible gravitational landscape, following the troughs and ridges imprinted by inflation. The densest knots eventually collapsed to form the first stars and galaxies, while the underdense regions, the valleys in that early landscape, were left behind, expanding into the vast cosmic voids we see today. This means the majestic filaments and cavernous voids of the cosmic web are not an accident. They are the direct, grown-up descendants of those microscopic quantum ripples. The pattern we map across billions of light years is a fossil, a colossal imprint of the universe's first moment. When astronomers compare the pattern of hot and cold spots in the cosmic microwave background to the distribution of galaxies in modern surveys, they find a remarkable correspondence. The statistical signature of the seeds matches the statistical signature of the grown structure. It is a direct link, a chain of cause and effect stretching across nearly 14 billion years. So, mapping the cosmic web does more than just chart where galaxies are today. It allows us to perform a kind of cosmic archaeology. By studying the intricate details of the web's filaments and clusters, scientists can work backwards, testing theories about how inflation worked and what those primordial quantum fluctuations were like. Each new, detailed map of the large-scale structure adds another piece to the puzzle of our ultimate origins, telling us not just how the universe is built, but how it was born. The web connects more than just galaxies. It connects our present understanding directly to the universe's first unimaginable instant. The early universe was not silent. It was filled with a deep, resonant hum. In the seething plasma of the first few 100,000 years, a cosmic symphony played out. Ordinary matter, which scientists call baryonic matter, was coupled with light in a dense, opaque fog. Within this hot fluid, gravity pulled matter inward, while the intense pressure of radiation pushed it outward. This tug-of-war created colossal sound waves, pressure oscillations that rippled outward from every slight overdensity like the expanding rings from a stone dropped in a pond. These were the Baryon acoustic oscillations, and they would leave a permanent stamp on the cosmos. Then, at the 380,000-year mark, the universe cooled enough for atoms to form. Light suddenly decoupled from matter, streaming free to become the cosmic microwave background we observe today. In that instant, those rippling sound waves froze in place like a recording suddenly paused. The result was a subtle, spherical shell of matter surrounding each of those original density seeds, a fossilized echo of that primordial sound. This created a very specific preferred scale in the universe, a standard ruler etched into the fabric of reality. Today, that ruler measures about 500 million light-years across. This means that when we look at the distribution of galaxies, we find a slight but statistically significant tendency for them to be separated by this exact distance. It is not that every pair of galaxies is 500 million light-years apart, but that if you analyze millions of them, this specific scale emerges from the data as a faint, repeating signal. This is the gift of Baryon acoustic oscillations. They provide a fixed measuring stick of known length that we can use anywhere in the observable universe. By conducting massive galaxy surveys like the Baryon Oscillation Spectroscopic Survey, astronomers can search for this signature scale in the clustering of galaxies at different distances, and thus from different eras of cosmic history. Finding it is like discovering a grid of perfect squares superimposed over a vast, complex landscape. If the squares appear smaller than expected at a certain distance, it tells us the universe was more compact in the past, giving us a direct measure of how much it has expanded. If the pattern is distorted in a specific way, it reveals how the dark matter web has stretched or compressed over time. This makes Baryon acoustic oscillations one of our most powerful tools for precision cosmology. They act as a geometric backbone for the cosmic web, allowing us to measure vast distances independently of other methods and to trace how the web's growth has changed across billions of years. Most importantly, this fossilized sound wave helps us measure the influence of dark energy, the mysterious force accelerating the universe's expansion. By seeing how the standard ruler's apparent size changes over cosmic time, we can chart how quickly the universe has been stretching at different epochs, putting the effect of dark energy into sharp relief. It is a profound thought that the faint statistical whisper of galaxy positions today carries the imprint of sound waves from a time before a single star had ever shone. This is not just mapping structure, it is measuring the universe's heartbeat across time itself, using a rhythm set in motion during its first fiery moments. Where the great filaments of the cosmic web intersect, the universe builds its grandest cities. Galaxy clusters are the colossal gravitational anchors of this network, containing not hundreds, but often thousands of individual galaxies all bound together in a single, sprawling metropolis. Our own Milky Way is part of a modest local group, but a true cluster like the famous Coma cluster, visible in our night sky, is a different beast entirely. It is a seething swarm of over 1,000 galaxies, held in a mutual gravitational dance across millions of light-years. Yet, the galaxies themselves are only the visible tip of a much more massive iceberg. For every pinprick of starlight, there is vastly more in the form of two invisible components, a gargantuan halo of dark matter that provides the gravitational glue and an immense diffuse ocean of superheated gas. This intracluster gas is so incredibly hot, tens of millions of degrees, that it does not shine in visible light. It glows fiercely in X-rays. To our X-ray telescopes, a galaxy cluster is not a collection of stars, but a brilliant, amorphous cloud of incandescent plasma, revealing where the true bulk of ordinary matter in these structures resides. The formation of a cluster is a slow cosmic crescendo. Over billions of years, the dark matter filaments act as vast cosmic highways, funneling galaxies and gas toward their intersections. As this material flows in, it collides and merges in events of almost unimaginable violence. When two clusters collide, the resulting energy release is beyond comprehension, equivalent to the simultaneous detonation of billions upon billions of supernovae. These mergers are so powerful they can temporarily separate the different components of a cluster, the dark matter, the galaxies, and the hot gas, allowing us to study each one independently. In a sense, a massive cluster collision is a controlled experiment in universal physics conducted on a million light-year scale. This makes clusters far more than just destinations on our map. They are active laboratories. By studying the distribution and temperature of the hot gas, we can weigh the entire cluster and measure the shape of its dark matter halo, testing our theories of gravity itself. By counting clusters of different masses across cosmic time, we get a critical census. If the universe had more dark matter or a different expansion history, it would have formed more massive clusters or formed them earlier than what we actually observe. So each massive cluster, like the distant and aptly nicknamed El Gordo, or the Fat One, serves as a crucial data point. Its very existence, its mass, and its location tell us about the strength of the gravitational forces that built the web and the rate at which the universe has been expanding. They are the brightest beacons in the dark matter network, not because of their starlight, but because of the profound gravitational stories they tell. Mapping them precisely is like charting the capital cities on a continent, revealing not just where the population is concentrated, but the economic and historical forces that shaped the entire land. Between the brilliant superhighways of the cosmic web lie deserts of almost incomprehensible emptiness. These are the cosmic voids, the vast negative spaces that give the universe's structure its stark, dramatic relief. If galaxy clusters are the glittering metropolises, voids are the sprawling, silent wilderness between them, regions so immense they can span hundreds of millions of light years. Our own Milky Way galaxy, for all its hundreds of billions of stars, resides on the sloping border of one such void, a place astronomers call the local void. From our position, we are looking out across a cosmic abyss, a frontier of profound nothingness that stretches for at least 150 million light years. It is a humbling thought that one wall of our galactic home faces a near emptiness so vast it defies human scale. Yet to call a void completely empty is a misconception. They are not perfect vacuums. Within these colossal bubbles, you might find a handful of isolated, lonely galaxies, adrift like single ships on a dark, placid ocean. There is also an extremely diffuse mist of hydrogen gas, so thin it is almost undetectable, but the density of matter here is far, far lower than the cosmic average. This profound emptiness is not an accident, it is a fundamental feature. The voids are the inverse imprint of the web's creation. As gravity pulled matter into the filaments and clusters over billions of years, it drained these regions, leaving them behind as expanding bubbles of underdensity. They are the excavated pits left after the mountains of the web were built. This makes mapping the voids just as critical as mapping the clusters. By measuring their sizes, their shapes, and how they have grown over cosmic time, scientists gain a powerful probe into the forces shaping the universe. The growth rate of a void is exquisitely sensitive to the presence of dark energy. Think of the universe as a rising loaf of raisin bread. The raisins are the galaxy clusters. As the dough expands, the raisins move apart, but if there are large, airy bubbles in the dough, those voids will expand even faster than the dough itself, pushed outward by the pressure of the denser material around them. By observing how quickly cosmic voids grow, we can measure the push of dark energy against the pull of gravity. The galaxies that do, against all odds, form inside these voids offer another fascinating clue. Isolated from the dense, violent environment of clusters and filaments, these void galaxies often develop differently. They tend to be smaller, slower to form stars, and can exhibit odd, irregular shapes like cosmic hermits that have evolved in solitude. Studying them is like studying life in a deep desert oasis, revealing how a galaxy's environment, or lack thereof, dictates its evolution. These vast, empty expanses remind us that the cosmic web is a dynamic structure defined by both incredible congregation and profound absence. The emptiness is not a backdrop, it is an active player, its expansion helping to drive the flow of the universe. To understand the full story, we must listen to the silence of the voids as intently as we study the light of the clusters. These vast digital universes are not science fiction. They are the essential proving grounds for our understanding of the cosmic web. Before a single telescope points to the sky to map a filament, scientists first build the universe inside a supercomputer. Projects with names like Illustris TNG and Eagle are not just visualizations, they are entire synthetic cosmos, born from equations and evolved over billions of simulated years. They begin with a smooth, early universe, seeded with the same tiny quantum fluctuations we see in the cosmic microwave background. Then they set the rules, the known laws of physics, gravity, hydrodynamics, the behavior of dark matter and ordinary gas. With these rules in place, they press play and watch as a virtual cosmos unfolds from the Big Bang to the present day. The scale is staggering. These simulations track the evolution of trillions of particles representing dark matter, while also modeling the complex life cycle of ordinary matter, the birth of stars within collapsing gas clouds, the explosive deaths of supernova, and even the ravenous growth of supermassive black holes at the hearts of galaxies. The goal is breathtakingly ambitious: to grow a universe that looks, in its statistical properties, exactly like our own. The visualizations they produce are more than just beautiful, they are a direct window into processes we could never witness in real time. We can watch a dark matter filament slowly condense out of the primordial haze, see rivers of gas flow along it, and witness galaxies spark to life at the intersections. We can observe galaxy clusters, those massive cities, in violent collisions that unfold over hundreds of millions of years, compressed into a few minutes of simulation time. We can see how the furious energy from a central black hole, shooting out jets of plasma, can heat the surrounding gas and actually stifle star formation in an entire galaxy, a process called feedback that is crucial for explaining why the universe looks the way it does today. But these simulations are not just for show, they serve a critical scientific purpose as a cosmic testing ground. Scientists can run the simulation over and over, each time tweaking a single parameter. What if dark matter was slightly warmer? What if dark energy was a little stronger? What if gravity behaved differently on the largest scales? Each tweak produces a different cosmic web, a different pattern of filaments, clusters, and voids. Then, astronomers can take the actual maps from surveys like the Sloan Digital Sky Survey and compare them to these many simulated universes. The simulation, whose large-scale structure most closely matches our observed reality, tells us which set of cosmological parameters is most likely correct. It is a process of universal matchmaking, finding the digital twin that best fits our own cosmos. In this way, supercomputer simulations act as the crucial bridge between raw data and deep understanding. They help us interpret the faint signals from gravitational lensing. They give context to the statistical whisper of Baryon acoustic oscillations, and they predict what our next generation of telescopes should see when they peer even deeper into the cosmic web. They are, in essence, digital oracles, allowing us to run experiments on the universe itself, experiments that would be impossible any other way. The filaments of the cosmic web are not just dark matter skeletons, they are flowing with rivers of fuel. Between the glittering galaxies lies a vast, diffuse ocean of gas, a primordial substance known as the intergalactic medium. This is not the cold, dark emptiness it appears to be. It is a warm, ionized fog of hydrogen and helium, the raw material from which every star in every galaxy was originally forged. This gas permeates the filaments, acting as a cosmic reservoir, a continuous supply line feeding the growth of galaxies across billions of years. To understand the web as a living, evolving structure, we must learn to see this invisible bloodstream. But how do you map something so tenuous it contains only a few atoms per cubic meter, a vacuum far emptier than anything we can create in laboratories on Earth? The answer involves using the universe's most brilliant lighthouses as cosmic flashlights. Astronomers turn to quasars, the fiercely luminous cores of distant galaxies where supermassive black holes are actively feasting. A quasar can outshine an entire galaxy, its intense beam of light traveling across the universe for billions of years. As this piercing light journeys toward us, it passes through the filaments of the cosmic web. Atoms within the intergalactic gas absorb very specific wavelengths of that light, leaving behind a unique fingerprint, a series of dark absorption lines in the quasar's rainbow-like spectrum. Because the universe is expanding, gas at different distances is redshifted by different amounts, so each absorption line corresponds to a specific slice of space along that incredibly long line of sight. The result is not a picture but a barcode of the cosmos. A single quasar spectrum reveals dozens, sometimes hundreds of these lines, a dense thicket astronomers call the Lyman alpha forest. Each line is a whisper from a wisp of hydrogen gas in a filament somewhere between the quasar and us. By collecting the spectra from thousands of quasars in different directions, scientists can perform a kind of cosmic tomography. They stitch together these one-dimensional probes, using statistics and sophisticated models to reconstruct a three-dimensional map of where the gas is concentrated. This reveals the filamentary network in a whole new light, not by the galaxies that dot it, but by the diffuse fuel that constitutes its bulk. This mapping reveals the dynamic life of the web. We can see how this primordial gas, cooled and condensed by gravity, flows along the filaments into the waiting gravitational wells of galaxies, fueling new generations of stars. But the story does not end there. The map also shows how the gas is heated and transformed. When a massive star explodes as a supernova, or when a quasar unleashes a torrent of energy, they blast heavy elements like carbon and oxygen back out into the intergalactic medium. These events create powerful shock waves that heat the gas, preventing it from cooling too quickly and collapsing into new stars all at once. This feedback loop is crucial. It regulates the growth of galaxies and enriches the entire web with the seeds of planets and life. So, the faint absorption lines in a quasar's light tell a grand tale of cosmic circulation, of birth, death, and rebirth on a universal scale. They show us the web is not a static sculpture, but a vibrant, breathing system where matter is constantly recycled, connecting the fate of distant quasars to the very building blocks inside us all. The map we have is about to be redrawn in breathtaking detail. We stand on the cusp of a new age of cosmic cartography, where our ability to see the web will be transformed by a fleet of next-generation observatories, each designed to survey the heavens on an unprecedented scale. This is the era of the mega survey, where we will not just study the universe, we will take its census. Leading this charge from the ground is the Vera C. Rubin Observatory in Chile, with its monumental legacy survey of space and time. For 10 years, its massive mirror and camera will scan the entire southern sky every few nights, not once but over and over. It will not simply take a snapshot, it will create a cosmic movie capturing changes and movements across the firmament. This relentless observation will catalogue tens of billions of galaxies and measure the subtle gravitational lensing distortions of countless more, creating a weak lensing map of such immense statistical power that the dark matter web will appear in sharper relief than ever before. Meanwhile, from a vantage point a million miles from Earth, the European Space Agency's Euclid Space Telescope is already at work. Its mission is singular and profound: to map the geometry of the dark universe. By combining exquisitely precise measurements of both gravitational lensing and the clustering of galaxies across 10 billion years of cosmic history, Euclid will trace the influence of dark matter and dark energy with the precision of a master surveyor. It aims to answer a fundamental question: how has the growth of the cosmic web been accelerated or suppressed over time by these invisible forces? Soon, it will be joined by NASA's and Nancy Grace Roman Space Telescope, a wide-field observatory with a heart as large as Hubble's but a view over 100 times wider. Roman will perform sweeping infrared surveys, peering through cosmic dust to see the universe's large-scale structure during its most formative epochs. It will discover thousands of new exoplanets, but its core cosmological mission is to measure the effects of dark energy with multiple, independent methods, providing a cross-check on our understanding of the universe's expansion. Together, these instruments represent a collective leap in perception. They will generate not gigabytes but petabytes of data, a flood of information so vast it will require new branches of data science to interpret. The result will be the most detailed three-dimensional atlas of the cosmos ever conceived, a map so rich it will show not just the major filaments and voids, but the finer threads and tributaries within them. We will see the web's structure with finer resolution and deeper into the past, observing its infant form when the universe was only a fraction of its current age. This map promises more than just a better picture. It holds the keys to profound mysteries. By measuring how the web's clustering has changed with exquisite precision, scientists hope to finally pin down the nature of dark energy, determining if it is a constant force or something that varies over time. The data may even reveal the mass of neutrinos, those ghostly subatomic particles that stream through the web. By seeing how their collective gravity has subtly inhibited the growth of the smallest cosmic structures. We are building the instruments that will write the next chapter in the story of our universe, a chapter based on a map of everything. Your cosmic address determines your destiny. The intricate filaments and cavernous voids of the web are far more than a beautiful pattern. They are the ultimate environment, a cosmic ecosystem that actively writes the life story of every single galaxy within it. This is nature versus nurture on the grandest possible scale, where the invisible architecture of dark matter dictates whether a galaxy will blaze with newborn stars or fade into a quiet, red retirement. To understand a galaxy, you must first locate it on the universal map. Take a massive galaxy cluster, one of those dense metropolitan hubs. The environment here is extreme and violent. Galaxies whip past each other at tremendous speeds, their mutual gravitational pull stretching them into strange shapes during close encounters. But the real transformative force is the seething ocean of superheated gas that fills the cluster, the intracluster medium we discussed earlier. As a spiral galaxy, rich with cool gas for making stars, falls into this dense environment, it experiences a phenomenon called ram pressure stripping. Imagine holding a delicate dandelion seed head out the window of a speeding car. The rushing wind strips away the fluffy seeds. In a cluster, the galaxy is the dandelion, and the hot intracluster gas is the hurricane force wind. This process can efficiently blow away a galaxy's precious star-forming fuel, leaving it gas-poor and unable to create new stars. Over time, its existing, aging stars give it a reddish glow, and its structure smooths into an elliptical shape. This is how vibrant spiral galaxies are transformed into what astronomers call red and dead ellipticals, their star-forming lives cut short by a hostile urban environment. Now follow a filament out from that chaotic cluster into the quieter suburban regions. Here, along the dark matter threads, the conditions are far more serene. A galaxy like our own Milky Way resides in such a place, on a filament feeding into a modest group of galaxies. In this environment, the galaxy can gently and steadily accrete fresh hydrogen gas from the intergalactic medium flowing along the filament. This continuous supply of cold fuel allows for the sustained, orderly formation of new stars in a rotating disk, maintaining the classic spiral structure for billions of years. The filament is not just a road, it is a pipeline delivering the sustenance needed for a long and productive life. Venture even further into the deep solitude of a cosmic void. Here, a rare, isolated galaxy evolves in profound isolation. Cut off from the dense flows and violent interactions, its evolution is slow and preservationist. It may hold onto its original gas for much longer, but without fresh inflows or mergers to trigger vigorous star formation, it often becomes a time capsule dominated by an ancient population of stars. It is a cosmic hermit telling a story of quiet survival in the emptiness. By mapping the web across different epochs, astronomers can now trace this environmental influence through time. They can observe how galaxies in the young, still-forming web behave differently than those in the mature structure we see today. This research connects the largest and the smallest scales imaginable, linking the fate of individual stars and planets directly to the gravitational topography of the entire universe. The light from a single star in a distant spiral arm is in part a consequence of the dark matter filament that fed its galaxy. Our place in the cosmic web did not just give us a view, it made us what we are. This three-dimensional map is not a static image, but a history book written in light. To build it, astronomers must measure not just where a galaxy is on the two-dimensional dome of the sky, but crucially how far away it lies. The key to unlocking this third dimension is found in the very color of a galaxy's light. As the universe expands, it stretches the wavelengths of light traveling through it, shifting them toward the red end of the spectrum. This is cosmological redshift, and it acts as a universal odometer. The greater the redshift, the faster the galaxy is moving away from us, and because the universe's expansion is remarkably uniform on these vast scales, that speed translates directly into distance. A galaxy with a high redshift is not just far away in space, it is far away in time, its light a messenger from a younger cosmos. Capturing this redshift for millions of galaxies is the monumental task of spectroscopic surveys. Instruments like those used in the Sloan Digital Sky Survey employ ingenious arrays of hundreds of thin fiber optic cables, each one positioned by a robot to capture the light from a single, pre-identified galaxy in the telescope's field of view. In a single night, these fibers can drink in the light of thousands of galaxies, splitting their glow into a rainbow spectrum that reveals the distinctive fingerprint of redshift. Night after night for years, this painstaking work accumulates, building a point cloud of the cosmos. Each galaxy becomes a single, luminous pin in a growing three-dimensional model that stretches billions of light-years deep. Yet this map is fraught with profound complexity. First, there is the sheer, overwhelming volume. Modern surveys catalog hundreds of millions of galaxies, a data deluge that requires supercomputers just to store and sort. Then there are the observational biases. Our telescopes can only see the brightest objects at the farthest distances, meaning our map might miss faint, dwarf galaxies that trace the finer threads of the web. We must correct for these selection effects, statistically inferring what we cannot directly see. most mind-bending of all is the light travel time puzzle. When we look at a galaxy 1 billion light-years away, we are seeing it as it was 1 billion years ago. A filament of the web that appears to connect 2 points in our map might not even exist in that configuration today. One of its galaxies may have moved along the cosmic current in the eons it took its light to reach us. We are not looking at a snapshot of the present, but a layered composite of the past, like reading a biography where every chapter arrives out of order. To understand the web's true shape and how it has evolved, cosmologists must become master chronologists, untangling this four-dimensional knot by comparing the structure seen at different redshifts, different epochs. They use sophisticated computer models to essentially run the universe's expansion in reverse, calculating how those distant, ancient structures would have matured and shifted to become the web we see closer to home. It is a reconstruction of history from fragmentary, time-stamped evidence, a detective story written across the deepest fields of space. The universe's first baby picture holds the ultimate treasure map. This is the cosmic microwave background, a faint glow that fills the entire sky, the relic radiation from a time when the cosmos was a mere 380,000 years old. While it appears as a nearly uniform haze, satellites like Planck have mapped it with exquisite precision, revealing a tapestry of minute temperature fluctuations, mere millionths of a degree differences between one patch and another. These are not random imperfections. They are the gravitational seeds from which the entire cosmic web would grow, the initial conditions of the universe imprinted in light. By studying this pattern, scientists can read the fundamental properties of reality, the geometry of space, the total amount of matter and energy, and the precise recipe of ordinary matter, dark matter, and dark energy that would shape everything to come. This ancient map is the starting point for every supercomputer simulation of the cosmos, the opening frame in the universe's 14 billion-year film. But the connection runs deeper than just a starting point. There is a direct, measurable link between this ancient light and the galaxy filaments we map today, a phenomenon known as the integrated Sachs-Wolf effect. As photons from the cosmic microwave background travel for billions of years on their journey to us, they pass through the evolving gravitational landscape of the growing cosmic web. When a photon falls into a deep gravitational well, like that of a massive cluster, it gains energy, appearing slightly hotter. When it climbs out of a well that has become shallower due to the universe's expansion, it loses energy, appearing slightly colder. This subtle imprint means the patterns in the cosmic microwave background carry a faint echo of the large-scale structure that formed later in cosmic history. To detect this, cosmologists perform a cosmic cross-check. They take the exquisitely detailed temperature map from the Planck satellite and overlay it with three-dimensional maps of galaxies from surveys like Sloan. By analyzing the statistical correlation between the two where hot or cold spots in the ancient light align with the positions of modern filaments and voids, they can trace the growth of the gravitational wells over time. This is a direct probe of dark energy. If the universe were dominated only by matter, those gravitational wells would remain constant, and this specific correlation would be weak. But because dark energy is accelerating the expansion, it causes those wells to shallow out as the photons pass through, creating a detectable signal. Finding that correlation is like discovering a hidden watermark on the universe's first photograph, a watermark that only appears because of how the cosmos aged. So, the cosmic microwave background is more than a snapshot of infancy. It is a living document. It provides the original blueprint and then, through these subtle effects, also bears witness to the construction of the entire cosmic edifice that followed. It ties the smooth, hot universe of the past directly to the clumpy, structured web of the present, offering a single, continuous story written in the oldest light there is. The cosmic web may hold structures so vast they defy our current understanding of the universe. In the quest to map its grandest features, astronomers have identified potential candidates that push the very limits of scale, structures whose existence seems to challenge the foundational rules of cosmology itself. One of the most staggering is known as the Hercules-Corona Borealis Great Wall. This is not a wall of stone or ice, but a colossal filament of galaxies, an immense thread in the cosmic tapestry, estimated to stretch for an astonishing 10 billion light-years. To comprehend that distance, consider that the entire span of our observable universe is only about 93 billion light-years across. This single structure would therefore account for more than 10% of the entire observable cosmos. Its discovery did not come from mapping galaxies directly, but from tracing the most violent explosions in the universe, gamma-ray bursts. These fleeting, brilliant flashes are thought to mark the deaths of massive stars and the mergers of neutron stars. A team of astronomers noticed an unusual, dense concentration of these bursts in the directions of the Hercules and Corona Borealis constellations. They proposed that this cluster was not random, but instead traced an underlying, gargantuan concentration of galaxies too faint and distant to see directly, a structure of such immense proportions it was dubbed a Great Wall. The controversy arises because the apparent size of this wall seems to violate a cornerstone of modern cosmology, the cosmological principle. This principle states that on the largest scales, beyond a certain point, the universe should look roughly the same in all directions and be smooth without structures dominating the cosmos. The theoretical maximum size for a structure is calculated to be around 1.2 billion light-years. The Hercules-Corona Borealis Great Wall, at nearly 10 times that scale, appears to be an impossible outlier. If confirmed, it would mean one of two profound things. Either our understanding of the early universe and how the cosmic web forms is fundamentally incomplete, allowing for such monstrous filaments to grow, or the cosmological principle itself may need revision, suggesting the universe is not as uniform as we thought even on its grandest scales. This places the wall at the fiery frontier of cosmic discovery. Mapping and confirming such megastructures is incredibly difficult, as they lie at the very edge of our observational reach, their faint light mixed with the glow of closer objects. The debate continues, with some scientists proposing alternative explanations for the gamma-ray burst data. Yet, the very possibility of its existence serves as a powerful reminder. Our map of the cosmic web is still a work in progress, sketched with the uncertain lines of distant, ancient light. The universe may yet hold surprises colossal enough to reshape the foundations of our cosmic address, waiting in the darkness between the constellations for our next generation of telescopes to reveal them. Every map of the cosmos is also a journey into the past. The light from a distant galaxy is a messenger that has been traveling for millions, even billions of years, carrying a portrait of the universe as it was when that light first began its voyage. When we plot a galaxy on our three-dimensional chart, we are not just marking a location in space, we are pinning a moment in time. This is the profound gift of look-back time, a consequence of the finite, though incredible, speed of light. It means our grand map of the cosmic web is not a single snapshot of the present, but a layered composite, a collage of different eras stacked upon one another. A brilliant cluster 5 billion light-years away is not showing us what it looks like today. It is revealing its adolescent self from 5 billion years ago, a time when our own solar system was just a swirling cloud of gas and dust. This transforms our atlas into a time machine, allowing us to watch the universe grow up. By constructing separate maps of the nearby universe and the distant universe, astronomers can directly observe the evolution of the web's architecture. Compare a map of galaxies within a few 100 million light-years, which shows the modern, mature web, to a map of galaxies several billion light-years away, which shows the web in its younger, more formative state. The differences are dramatic. In the distant, early maps, the filaments appear thinner, more tenuous, like the first delicate threads of a spiderweb just beginning to form. The great clusters are smaller and less frequent, still gathering their members from the flowing cosmic currents. The voids, meanwhile, are not as profoundly empty, still containing more stray gas and galaxies that have not yet been fully drained away by gravity's pull. Watching these maps change across cosmic time is like flipping through the pages of a photo album of the universe. We see the filaments thicken and strengthen as more dark matter and gas flow into them. We witness the epic, slow-motion mergers of galaxy clusters, the violent events that build the metropolitan hubs of the cosmos. We observe the voids expand and clarify as the last remaining matter is siphoned away into the surrounding network. This four-dimensional mapping, adding the crucial axis of time to the three of space, is the ultimate test for our theories of cosmic structure. The computer simulations that start with the early universe must end up producing not just the web we see around us today, but every stage of it we observe in our deep look-back maps. When they match, it confirms our understanding of the fundamental forces at play. This dynamic history reveals the patient, relentless work of gravity across nearly 14 billion years. It shows us the transformation from a nearly smooth, hot primordial soup, revealed in the cosmic microwave background, into the spectacularly complex and clumpy network we call home. Every filament, every cluster, every void has a biography written in the expanding space between galaxies. Our place in this evolving tapestry is not static. We are on a moving platform within a living structure. The local filament that feeds our galaxy group is still subtly shifting, and the great void next door is still slowly growing. To hold a map of the cosmic web is to hold a story of becoming, a narrative of construction on the grandest possible scale, where the past is visibly layered across the heavens for anyone who knows how to look. The cosmic web's magnificent architecture is not a permanent monument. As we trace its history through deep time, we must also confront the force that will dictate its ultimate destiny, a shadowy power known as dark energy. This is not a force we can see or touch, but its signature is written across the expansion of the universe itself. For billions of years, gravity was the master sculptor, patiently gathering matter into filaments, clusters, and walls. Now a new era has begun. Dark energy is causing the very fabric of space to stretch at an ever-increasing rate, a cosmic acceleration that is fundamentally reshaping the future of the web. Imagine two galaxies on opposite ends of a filament, connected by that river of dark matter. In the past, gravity's pull would have drawn them closer together over immense timescales. Now, the expansion of space between them is accelerating, acting like a relentless current pulling them apart. This creates a profound cosmic tug of war, with dark energy's push now rivaling gravity's historic pull. The consequences for the web are profound and slow-moving but inevitable. In the distant future, perhaps hundreds of billions of years from now, the accelerating expansion will begin to win. The great filaments, those superhighways of the cosmos, will start to stretch and thin. The flow of fresh, cold gas from the intergalactic medium along these threads will slow to a trickle and then stop entirely. Galaxies will be cut off from their fuel supply, their star formation ceasing as they consume the last of their internal reserves. The bustling metropolitan galaxy clusters will not vanish, but they will become isolated islands. The galaxies within them will remain bound by their mutual gravity, but every cluster will be rushing away from every other cluster, lost in an ever-widening sea of expanding space. The cosmic web will not be torn apart instantly, but it will be pulled taut, its connections severed, its grand network of relationships slowly fading into isolation. This is why mapping the growth of structure today is so critically important. By precisely measuring how quickly galaxy clusters are moving apart and by studying how the web's architecture has evolved from the past to the present, cosmologists can measure the strength of dark energy's push. It is like taking the universe's vital signs, listening to the rhythm of its expansion to diagnose its long-term fate. Each new, detailed map from observatories like Euclid and the Variance. Rubin Observatory adds another data point to this cosmic forecast. The story of the cosmic web, therefore, is a story of two opposing forces. One, gravity, builds connection and structure, weaving the universe together. The other, dark energy, drives separation and isolation, stretching the tapestry thin. Our universe exists in the fleeting balance between these two giants, in the era where the web is still visible and whole. To understand this balance is to glimpse the ultimate fate of everything we see, a future written not in fire or ice, but in the silent, accelerating stretch of space itself. Yet another ghostly traveler leaves its mark on the cosmic web. Billions of neutrinos pass through your body every second, a silent rain from the sun and distant cosmic events, yet you feel absolutely nothing. These are among the most elusive particles in existence, with barely any mass and no electric charge, allowing them to fly through planets and stars as if they were empty space. Born in the furnace of the Big Bang and in the hearts of stars, they are cosmic spectators, yet their collective journey has subtly shaped the grand architecture we are mapping. Because neutrinos possess a tiny bit of mass and move at velocities approaching the speed of light, they exhibit a behavior physicists call free streaming. Imagine a vast crowd trying to form a tight, orderly circle, but within that crowd are countless individuals who simply cannot stand still. They are constantly, gently jostling their neighbors, preventing the crowd from becoming perfectly dense and compact. On a cosmic scale, this is what neutrinos did in the early universe. Their relentless, high-speed motion acted as a smoothing force, smearing out the very tiniest wrinkles in the density of matter. This means the cosmic web we see today is missing its finest threads. The smallest dark matter halos, those that in a neutrino-free universe might have hosted tiny, faint dwarf galaxies, were never able to fully form. Instead, the gravitational landscape was subtly leveled on the smallest scales, like a gentle cosmic iron passing over the finest details of the tapestry. This leaves a distinct statistical signature in the web's clustering, a slight deficit of ultra-fine structure that sophisticated maps can, in theory, detect. Finding this signature is one of the next great challenges in cosmology. Future surveys like the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope aim to create maps of such exquisite detail and statistical power that they can measure the precise way matter clumps together across different scales. Within that data, like a faint watermark, may lie the imprint of neutrino-free streaming. Detecting it would be a monumental convergence of scales. It would mean that by charting the universe's largest structures, spanning billions of light-years, we have created a sensitive enough instrument to measure the influence of one of the smallest, most ghostly particles. This would do more than just confirm a piece of cosmic history. It could allow scientists to finally pin down the absolute mass of neutrinos, a fundamental mystery that has eluded particle physics experiments on Earth. The cosmic web, therefore, is more than a map of dark matter and galaxies. It is a historical record, etched by every actor in the cosmic drama, from the relentless pull of gravity to the gentle, smoothing flight of the universe's most elusive particles. The faintest whisper in the universe comes from a single, spinning electron. Every atom of neutral hydrogen, the most basic and abundant substance in the cosmos, emits a signature radio signal with a precise wavelength of 21 centimeters. Alone, it is imperceptible, but together, across the vast expanse of a cosmic filament, these whispers combine into a chorus. A powerful new mapping technique listens not for the brilliant soloists of individual galaxies, but for this collective hum of the raw material from which they are made. This is intensity mapping, a revolutionary way to chart the cosmic web by tuning into the radio song of hydrogen itself. Instead of painstakingly identifying and measuring each galaxy, astronomers use massive radio telescopes to capture the combined 21-centimeter emission from all the hydrogen gas within an enormous volume of space at once. It is like trying to map a forest not by counting every single tree, but by listening to the unified rustle of all its leaves in the wind. The expansion of the universe provides the crucial third dimension to this map. As space stretches, it also stretches the wavelength of this hydrogen signal, shifting it from radio waves toward longer, lower frequencies. By tuning their receivers across a wide band of frequencies, scientists can essentially slice the universe into layers. A higher frequency corresponds to hydrogen emission from gas closer to us, while a lower, more redshifted frequency comes from hydrogen in the far distant, early universe. This allows them to build a true three-dimensional map of where hydrogen gas is concentrated throughout cosmic history, directly tracing the filaments and voids regardless of whether they contain bright, easy-to-spot galaxies. Groundbreaking projects like the Hydrogen Epoch of Reionization Array, or HERA, are already listening for this signal from the universe's adolescence. The future Square Kilometer Array, a telescope with collecting area spanning continents, will turn this whisper into a shout, creating unparalleled maps of hydrogen distribution. This technique promises to illuminate the cosmic web in its purest form, showing us the scaffolding of gas before most stars had even ignited. It could reveal the intricate structure of the web during the cosmic dawn and through the epoch of reionization, that pivotal period when the first brilliant stars and galaxies flooded the universe with ultraviolet light, slowly burning away the primordial hydrogen fog. By comparing these radio maps of raw material to the optical maps of finished galaxies, we will see the full story of cosmic construction, from the quarry to the cathedral, revealing how the universe transformed diffuse gas into the glittering structures we call home. The universe's grandest structures may soon be traced not by light but by vibration. A new form of cosmic cartography is on the horizon, one that listens for the tremors in spacetime itself to map the architecture of everything. This is the promise of gravitational wave astronomy, when the most massive objects in the cosmos collide, when black holes with billions of times the sun's mass spiral together, or when dense neutron stars merge. They do not just flash with light. They shake the very fabric of reality, sending out ripples in spacetime that travel at the speed of light across the cosmos. These are gravitational waves, and they carry a unique story about the universe's most extreme events and the places where they occur. For decades, our map of the cosmic web has been painted with photons, particles of light. We have used visible starlight, X-rays from hot gas, and radio whispers from hydrogen. But gravitational waves offer a fundamentally different ink. They are not emitted from stars or gas. They are generated by the warping of spacetime itself due to colossal accelerations. This means they can travel to us from environments where light is trapped or obscured, from the deepest hearts of galaxy clusters or the earliest, darkest ages of the universe. Ground-based observatories like LIGO and Virgo have already opened this window, detecting waves from stellar mass black hole mergers. But the future holds an even more profound tool, the Laser Interferometer Space Antenna, or LISA. This ambitious mission, a trio of spacecraft flying in a giant triangle millions of kilometers apart, is designed to listen for the low-frequency hum of the universe's most massive mergers, events involving supermassive black holes that occurred when the cosmos was young. The revolutionary idea is this: the sources of these gravitational waves are not scattered randomly. The titanic black holes that generate them reside in the centers of galaxies. And galaxies, as we know, are strung along the filaments and clustered at the nodes of the cosmic web. Therefore, the distribution of gravitational wave events across the sky should trace out the same large-scale structure we see with light. By detecting thousands of these cosmic tremors and plotting their locations, scientists could create a statistical map of matter distribution, a gravitational wave census of the cosmos. This map would be independent, built from a completely different messenger. It would not rely on the brightness of a galaxy or the temperature of gas. It would rely solely on the spacetime ripples from the most violent gravitational engines. This independence is its greatest power. It provides a crucial cross-check. If the web mapped by gravitational waves aligns perfectly with the web mapped by light and dark matter inferences, it would be a triumphant confirmation of our entire cosmological model. But any discrepancy would be a flashing signal of something new, perhaps a misunderstanding of how supermassive black holes form and grow within the web, or even a clue about the nature of dark matter itself. Furthermore, these waves could peer into eras currently inaccessible. The first supermassive black holes likely formed and merged in the primordial darkness before the first stars flooded the universe with light. LISA could potentially detect the gravitational waves from those ancient mergers, allowing us to infer the distribution of matter in the infant cosmic web, mapping its structure in the universe's first billion years. We would be reading the blueprint by feeling the vibrations left by the construction, long before the lights were turned on. This is the next frontier of cosmic cartography, where we learn to see by listening, and where the silent tremors of black holes become our guides to the architecture of all existence. Our map of the cosmos is drawn from a single, unique vantage point. This simple fact introduces a profound and unavoidable limitation known as cosmic variance. We have only one universe to observe, and we are observing it from one specific location within it. The volume of space we can survey with our most powerful telescopes, while immense, is still finite. It is, in essence, a single sample taken from a potentially infinite whole, and like any single sample, it may not be perfectly representative. Think of trying to understand the global climate by measuring the weather in your own backyard for a single year. Your data would be real, but it might be skewed by a local drought or an unusually warm season, not reflecting the planet's broader patterns. Cosmic variance is the cosmological version of this sampling error. It means that the specific patch of the universe we can see might be atypical. Perhaps our galactic neighborhood, the local group, resides on the edge of an unusually large cosmic void, making our region seem emptier than the universal average. Or maybe we are positioned unusually close to a massive supercluster like Laniakea, which could distort our measurements of how quickly galaxies are streaming on the largest scales. This problem becomes most severe when we try to study the very largest structures, those approaching the size of the observable universe itself. At these colossal scales, we have only a handful, sometimes just one or two, independent samples within our field of view. It is incredibly difficult to tell if a giant filament or a vast void is a standard feature of cosmic architecture or a rare statistical fluke that just happens to be in our line of sight. Astronomers have developed clever strategies to combat this inherent uncertainty. They conduct surveys in multiple, widely separated directions across the sky, piecing together different samples to build a more complete statistical picture. They also create thousands of sophisticated computer simulations, each representing a different possible realization of a universe with the same underlying rules, and then compare our actual observations to this library of simulated cosmos. This allows them to estimate the range of possible outcomes and quantify the uncertainty in their measurements. Future missions like the Vera-C, Rubin Observatory's decade-long survey, will directly attack cosmic variance by mapping an unprecedented volume of the universe, increasing our sample size and giving us a much clearer view of the cosmic norm. Yet, a fundamental limit remains. We cannot step outside our universe to take a measurement from another angle. Cosmic variance is a humbling reminder that our magnificent map, for all its detail and grandeur, is still a local portrait. It is the best picture we can possibly take from our solitary seat within the cosmic amphitheater, a masterpiece of science that must always carry a footnote acknowledging the limits of our singular perspective. The iron in your blood and the oxygen in your lungs are not just elements, they are cosmic travelers. They began their journey within the fiery hearts of stars that lived and died long before our sun was born. But those stars themselves could not have formed without the grand architecture we have been mapping. The carbon, oxygen, and iron that compose our world were forged inside stellar furnaces that ignited only where the cosmic web provided the necessary conditions, within the dense gravitational wells of dark matter halos where gas could collect and collapse. This means the very chemistry of life is a direct product of the universe's large-scale structure. The web is not a distant spectacle. It is the foundational lattice upon which the possibility of our existence was built. Consider the specific, quiet suburb of the cosmos we call home. Our Milky Way galaxy is not adrift in a random sea. It is part of a flat, pancake-like assembly of galaxies called the local sheet, which is itself a filamentary thread within the vast Laniakea supercluster. This position within the web's architecture was crucial. It provided a stable, relatively peaceful galactic environment, shielded from the violent gravitational tides and gas-stripping winds of a dense cluster core. In that stable suburban lane, our particular solar system could coalesce from a cloud of dust and gas enriched by those earlier generations of stars. A planet could find a stable orbit around a steady star, and in the gentle conditions that followed, the complex chemistry of life could begin its long, slow experiment. This connection transforms the cosmic web from an abstract map into a narrative of origins. When we trace the filaments and voids, we are not just charting where things are, we are reading the history of how the universe organized itself to become complex and eventually conscious. The renowned cosmologist Carlos Frenk has reflected on this profound link, suggesting that we are the universe's way of knowing itself. Our ability to look up, to build telescopes, to create these maps, is a process that began with the quantum seeds of the Big Bang and unfolded along the dark matter filaments that gathered the material for stars, planets, and ultimately, minds. Understanding this vast network provides the ultimate context for our place in the cosmos. It suggests that the conditions necessary for life are not a random accident in an indifferent void, but are intricately woven into the universe's fundamental architecture. The same gravitational forces that sculpted the great walls and voids also gently guided the gas that formed our sun and the rocky planet beneath our feet. The map, therefore, stops being a mere scientific tool. It becomes a story, our story, written in the gravitational language of dark matter and illuminated by the billion-year-old light of ancestral stars. It tells us that we are not just observers of the cosmic web, we are its embodied expression, a fleeting but conscious part of its magnificent, evolving structure. Mapping the cosmos has become a collaborative project shared by millions. The sheer volume of data from modern sky surveys is so immense that no single team of professional astronomers could possibly process it all. This challenge has given rise to a beautiful partnership between science and the public, a movement known as citizen science. One of the most successful projects is Galaxy Zoo, which began with a simple, profound question. Could the human eye, with its innate pattern recognition, help classify the shapes of nearly 1 million galaxies? The answer was a resounding yes. Hundreds of thousands of volunteers from all walks of life, from schoolchildren to retirees, logged on to examine stunning images from the Sloan Digital Sky Survey. With a simple interface, they answered whether a galaxy was spiral or elliptical, noted the direction of its rotation, and even flagged strange and unusual objects. This collective effort created a massive, human-curated catalogue of galaxy morphology, a treasure trove for researchers studying how a galaxy's form is shaped by its place in the cosmic web. The data revealed clear patterns showing how spiral galaxies are more common along the quieter filaments, while elliptical galaxies dominate the violent cores of clusters, directly linking a galaxy's destiny to its environmental address. But the impact went far beyond data collection. In the process of classifying, these citizen scientists made genuine discoveries. Volunteers were the first to notice a class of small, greenish objects that didn't fit known categories. Their curiosity led astronomers to identify a new type of galaxy, now called green P galaxies, which are undergoing intense bursts of star formation and offer clues about the universe's early years. Other volunteers spotted rare overlapping galaxies and gravitational lenses that professionals had missed. This open data philosophy is a cornerstone of modern cosmology. The incredible data sets from major surveys are not locked away, they are released to the world. Any student with a laptop, any amateur astronomer with curiosity, can download the same images and spectra that professionals use. They can create their own maps, hunt for asteroids, or analyze the light of distant quasars. This democratization of cosmic cartography means that a breakthrough could come from a classroom or a home office as easily as from a major university. It transforms the public from passive observers into active participants in the greatest mapping project in history as we enter the era of the Variance. Rubin Observatory and other mega surveys, the data deluge will become a tsunami. Here, the legacy of citizen science takes a new form. The millions of classifications made by human volunteers over the years have become the perfect training set for machine learning algorithms. By learning from the collective intuition of hundreds of thousands of eyes, artificial intelligence systems can now be taught to scan new images, identifying and classifying galaxies at incredible speed and scale. The human touch trains the machine, which then extends our reach into the data ocean. This collaborative loop accelerates our ability to map the web's finer details and understand its evolution. Engaging the public in this way does more than speed up research. It builds a profound, personal connection to the cosmos. When you spend an evening classifying galaxies, you are not just looking at pretty pictures, you are directly contributing to our understanding of the universe's structure. You are touching the data, seeing the same celestial objects that grace scientific papers. This shared endeavor reminds us that the cosmic web is not just an object of study for a select few, it is a heritage of wonder for all of humanity. The map we are building belongs to everyone, drawn by the collective curiosity of our species looking up at the night sky and deciding to help chart its hidden depths. Our magnificent map of the cosmic web has a final, unbreakable border. There is a fundamental limit to how far we can ever see, a horizon written into the laws of physics and the history of the universe itself. This is the boundary of our observable universe, a spherical shell centered on our location, with a radius of about 46.5 billion light-years. That distance is not arbitrary. It is the maximum distance from which any signal, any particle of light, could have possibly reached us in the entire 13.8 billion-year history of the cosmos since the Big Bang. We call this the particle horizon, and it represents the ultimate edge of our knowledge. Every galaxy, every filament, every measurement in our grand three-dimensional atlas lies within this finite sphere. We cannot map anything beyond it, not because our telescopes are not powerful enough, but because the information from those regions has not had enough time to travel to us. The universe beyond that horizon is, by definition, disconnected from our causal past. It is a realm forever hidden, a part of the greater cosmos we can speculate about but never directly observe. This places a profound and humbling cap on our cosmic cartography. Our goal is not to map the infinite universe, but to create a complete and perfect census of everything within this one precious, observable volume. Yet, even this finite map is not stable. Due to the accelerating expansion driven by dark energy, the most distant galaxies we can currently see are not standing still. They are being carried away by the stretching of space itself at such a rate that their light, which is reaching us now from the distant past, will eventually be unable to reach us at all. They are crossing over our cosmic horizon, fading from view like ships disappearing over the curve of the Earth. This means the observable universe is not a fixed stage. It is slowly shrinking in terms of the number of galaxies we can ever hope to detect. The most ancient, faint threads of the web at the very edge of our vision are the first to vanish. Their light stretched into undetectable infrared wavelengths and then into nothingness as the expansion severs the connection entirely. For future cosmologists, billions of years from now, the night sky will be far emptier, their observable universe limited to the gravitationally bound local group of galaxies, with the rest of the cosmic web lost to an impenetrable darkness. This understanding transforms how we interpret our maps today. When we look at the most distant, redshifted galaxies, we are seeing a universe that is not only younger, but also one that represents a larger portion of the causally connected cosmos of that era. Our map is a time capsule layered with disappearing frontiers. It reminds us with absolute clarity that we are not mapping the universe. We are mapping our universe, the local patch of reality to which we are causally tethered. Everything we know, every law we have deduced, is based on this single sample. The cosmic web we trace so meticulously is the magnificent but finite architecture of our home within a totality whose full scale and shape may forever remain a beautiful, tantalizing mystery. There is an undeniable beauty in the map of everything. The visualizations born from supercomputer data are far more than analytical tools. They are stunning works of art, intricate tapestries woven from the laws of physics. We see tendrils of glowing gas tracing dark matter filaments, brilliant knots of galaxy clusters burning like cities seen from space, and profound voids of cosmic nothingness. These images possess a mesmerizing, almost organic quality, their patterns echoing those found throughout nature. The branching structure of a filament looks uncannily like a neural network in a human brain, or the sprawling root system of an ancient tree. It recalls the delicate tracery of veins in a leaf, or the branching patterns of lightning across a stormy sky. This visual resonance is not a mere coincidence. It points to a deeper truth about how universal physical principles, like the minimization of energy and the flow of forces along paths of least resistance, give rise to similar structures across vastly different scales from the quantum to the cosmic. This intersection of form has sparked profound dialogue between scientists and artists, who now collaborate to translate petabytes of cosmological data into immersive experiences. In planetariums around the world, audiences do not just hear about the cosmic web, they travel through it, fly through visualizations based on real simulation data, allow you to soar down a filament 100 million light-years long, to circle a colossal cluster where galaxies swarm like bees, and to drift into the heart of a void where the nearest galaxy is an impossibly distant speck. These are not animations in the traditional sense. They are navigable maps of reality, scaled down to human perception. Interactive art installations take this further, using light, sound, and sculpture to make the abstract architecture of the universe something you can feel in the room around you. This aesthetic dimension serves a vital purpose beyond spectacle. It engages a different part of our mind, the part that responds to pattern, scale, and sublime beauty. When a complex scientific concept is rendered with such visceral elegance, it bypasses intellectual barriers and sparks a direct sense of wonder. That wonder is a powerful catalyst for curiosity, drawing people into the science behind the image. It makes tangible the incredible truth that these are not artistic interpretations, but portraits of actual structures that exist out there, drawn from mathematical models of dark matter and the observed light of billions of galaxies. The profound beauty of the cosmic web map reminds us that our quest to understand the universe is not a cold, clinical dissection. It is often a revelation of inherent elegance. The same mathematical principles that describe the gravitational collapse of a galaxy cluster also govern the graceful curve of a Nautilus shell. There is a harmony in the laws of physics that resonates with human creativity, suggesting that in mapping the cosmos, we are also, in a way, appreciating a form of art authored by reality itself. This fusion of meaning and form invites us to see the universe not just as a place of fact, but as a realm of deep and stunning pattern. Gravity is not just the architect of the cosmic web, it is the theory we are putting on trial. For over a century, Einstein's general relativity has reigned supreme, describing how mass and energy warp the fabric of spacetime. Yet, the vast, dark scaffolding of the universe presents a monumental challenge. Could our understanding of gravity itself be incomplete? This question drives scientists to use the cosmic web as the ultimate laboratory, a testing ground for physics on a scale no Earth-bound experiment could ever achieve. Some researchers have proposed elegant alternatives to the dark matter hypothesis, theories with names like modified Newtonian dynamics or MND. The core idea is compelling. What if we simply do not understand how gravity works at the extremely low accelerations found in the outer reaches of galaxies? Perhaps a tweak to the laws of physics could explain why stars orbit so quickly without invoking an invisible substance. On the scale of a single galaxy, such modifications can be made to fit the data. But the universe does not operate on a single scale. The true test of any theory of gravity is whether it can build the cosmos we actually see from the ground up. This is where the detailed map of the large-scale structure becomes the judge. When scientists take a theory like MND and attempt to simulate the formation of the cosmic web over billions of years, they often run into profound difficulties. The delicate statistical patterns we observe, the specific way galaxies cluster along filaments, the sizes and distributions of the immense voids, the subtle shearing of light from gravitational lensing, these are the fingerprints left by the universe's growth. A successful theory must reproduce all these fingerprints simultaneously. So far, the standard model of cosmology, known as lambda-CDM for its inclusion of dark energy and cold dark matter, has been remarkably successful. Starting from the quantum seeds in the cosmic microwave background and applying only the known laws of physics and gravity as described by general relativity, supercomputer simulations of lambda-CDM grow a cosmic web that looks statistically identical to the one we map with our telescopes. The filaments, the clusters, the voids, they all fall into place. Alternative theories that modify gravity without dark matter often struggle to create this rich, observed structure. They might produce a web that is too clumpy or too smooth, with voids that are the wrong size or filaments that are too weak. The precise measurements from galaxy surveys and weak lensing maps provide a stringent set of constraints, ruling out entire families of theoretical alternatives. This makes cosmic cartography far more than a mapping exercise. It is a direct experiment in fundamental physics. By charting the distribution of matter across billions of light years, we are conducting a stress test on gravity itself. Every new, more detailed map from observatories like Euclid and the Variance, Rubin Observatory will tighten these constraints further, either solidifying our current model or perhaps revealing a subtle crack where a new theory of gravity could take root. The architecture of the universe, therefore, is not just a consequence of gravity, it is the most powerful evidence we have for what gravity truly is. Our own galaxy is a citizen of a modest cosmic community. The Milky Way does not drift alone through the void. It is a prominent member of a small gathering known as the Local Group, which includes the Great Spiral of Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies all bound together by mutual gravity. This entire assembly, spanning about 10 million light-years, is itself just a tiny knot, a minor intersection in the filaments of the cosmic web. To understand our place, we must zoom out further. Our local group is not floating in isolation. It is embedded within a larger, flattened structure called the local sheet, a wall of galaxies that acts like a single thread in the grand tapestry. And this thread is part of something truly immense, the Laniakea supercluster. The name Laniakea means immeasurable heaven in Hawaiian, and it is a fitting title for a gravitational continent containing over 100,000 galaxies across a span of 520 million light-years. Within Laniakea, every galaxy, including our own, is flowing along invisible gravitational currents toward a common center of mass, a great attractor near the dense Virgo cluster. This means the motion of our Milky Way is not random. It is part of a vast cosmic river. We are being pulled, along with Andromeda and every other galaxy in our local sheet, toward the Virgo cluster's immense gravity well. This grand flow is the local expression of the same dynamics that shape the entire web, the accretion of matter along filaments toward the densest nodes. We can now map this local architecture with stunning precision, thanks to missions like the European Space Agency's Gaia spacecraft. Gaia is not looking at distant quasars, it is performing a monumental census of our own galactic neighborhood, measuring the positions, distances, and motions of over 1 billion stars within the Milky Way with unprecedented accuracy. This data is like having a super high-definition global positioning system for our galaxy. By tracing the motions of these stars, astronomers can work backwards to understand the gravitational forces at play, mapping the distribution of dark matter within our own halo and precisely charting our galaxy's trajectory through the local group. This local map reveals a future written in gravity. The Milky Way and the Andromeda Galaxy are on a collision course, moving toward each other at about 110 kilometers per second. In roughly 4.5 billion years, these two great spirals will begin a slow, majestic dance, merging over billions of years to form a single, giant elliptical galaxy. This event is not a catastrophe. It is a natural and inevitable phase in the life of galaxies within a clustered environment, a direct consequence of our shared location within the local group's gravitational basin. And that entire group's motion is itself dictated by the larger architecture. The pull we feel toward the Virgo cluster is a gentle but persistent tide, a testament to the fact that even our massive galaxy is a speck in a much larger gravitational field. This local, detailed map serves as a crucial bridge in our understanding. It is a microcosm, a nearby laboratory where we can observe the same processes of accretion, merger, and flow that we see operating across the universe, but right in our own backyard. The intricate dance of the Magellanic Clouds around the Milky Way, the future merger with Andromeda, the steady drift of our entire local group, these are all small-scale echoes of the grand choreography of the cosmic web. They connect the ultimate fate of our own star and planet directly to the architecture of the universe on the largest scales, proving that we are not just observers of this vast network, but active participants moving along its ancient, invisible streams. These invisible magnetic threads are woven through the very fabric of the cosmic web. While gravity sculpts the grand architecture of filaments and voids, another, more subtle force also leaves its mark, a whisper-thin network of magnetic fields that permeates the vast spaces between galaxies. These fields are astonishingly faint, millions of times weaker than a common refrigerator magnet, yet they stretch across millions of light years, forming an electromagnetic skeleton within the gravitational one. They are not a mere afterthought but an active component of the cosmic ecosystem, a hidden layer of energy that influences how the universe evolves. The origin of these vast fields is one of cosmology's great puzzles. They are likely ancient, seeded in the turbulent plasma of the early universe, and then stretched and amplified over billions of years by the very motions that built the web itself. As rivers of gas flow along dark matter filaments and crash into forming galaxy clusters, they create immense turbulence like cosmic whirlpools. This churning motion can twist and strengthen primordial magnetic fields, much like a dynamo generates Earth's magnetic field. Within the intense environments of galaxy clusters, these amplified fields become trapped, weaving through the superheated gas and influencing everything within it. Their presence can be felt in subtle but profound ways. Charged particles like electrons and protons spiral along magnetic field lines. This means the paths of cosmic rays, those high-speed atomic fragments hurtling through space, are not straight lines but corkscrew journeys guided by this invisible lattice. The fields can also provide a form of cosmic pressure, helping to support the weight of gas in filaments and slowing its collapse into galaxies, thereby subtly regulating the pace of star formation across the universe. To map something so diffuse and weak, astronomers must use indirect and ingenious methods. One approach listens to a specific song of the universe, synchrotron radiation. When electrons spiral at near light speed around magnetic field lines, they emit a distinctive polarized radio whisper. By carefully measuring this faint radio emission and its polarization from large regions of space, scientists can trace the orientation and strength of the fields that guide those electrons. Another technique relies on a celestial lighthouse effect. As polarized light from a distant quasar or radio galaxy travels through the magnetized gas of the cosmic web, its polarization angle slowly rotates, a phenomenon known as Faraday rotation. The amount of rotation tells a story, revealing the strength of the magnetic fields along the line of sight and the density of the electrons within it. By observing this effect across thousands of distant sources, a statistical map of the magnetic web can begin to emerge. These magnetic fields are more than a physical force, they are a historical archive. Their patterns are a fossil record, encoding the history of violent astrophysical events over cosmic time. The energy from colossal galaxy mergers, the furious winds from supermassive black holes, the shock waves from supernova explosions, all these events inject turbulence and energy into the intergalactic medium, leaving their imprint on the magnetic field structure. By learning to read this magnetic fossil record, we gain a new window into the universe's energetic past, seeing not just where matter is, but how it has been stirred and energized across the ages. This adds a breathtaking layer of complexity to our cosmic maps. We are no longer just charting the distribution of mass, we are starting to trace the flow of energy. The universe is revealed not as a silent sculpture of dark matter and galaxies, but as a dynamic, magnetized organism, with forces both strong and subtle collaborating to write the story of everything we see. The final frontier of cosmic cartography is not a single telescope, but a grand synthesis. We are entering the age of multi-messenger astronomy, where the ultimate map of the web will be woven from threads of information no single instrument can provide. Each cosmic messenger, from ancient starlight to the faint tremor of a gravitational wave, tells a different part of the same story. By learning to read them all together, we will transform our understanding from a sketch into a living portrait. Think of it like diagnosing a patient. You would not rely on just a temperature reading or only an X-ray. You combine the blood test, the scan, the physical exam, and the patient's own description to get a complete picture of their health. The cosmic web is our patient, and we are finally learning to use its full medical chart. For a single galaxy cluster, this means layering observations like transparent sheets on a light table. The first sheet comes from optical telescopes, showing the glittering cities of individual galaxies. The second sheet is an X-ray image, revealing the immense, glowing ocean of million-degree gas that fills the cluster. The third sheet is a map of dark matter, reconstructed from the subtle gravitational lensing distortions of background galaxies. A fourth sheet might come from radio telescopes, tracing the faint, filamentary magnetic fields woven through the hot plasma. When these layers are aligned, they do not just show where things are, they reveal how the different components influence each other. We can see how the dark matter's gravity confines the hot gas, and how that gas, in turn, is shaped by its own internal magnetic pressure. A more dramatic example comes from the most violent events in the cosmos. Imagine a brilliant gamma-ray burst, a fleeting flash of high-energy light from a dying star in a distant galaxy. That flash pinpoints a specific location on the cosmic web, a single address in the vast tapestry. If that same cataclysm also produced a detectable ripple in space-time, a gravitational wave, that signal would provide an independent and exquisitely precise measurement of its distance. Combining these two messengers instantly places that event in our three-dimensional map with phenomenal accuracy, like getting both a street name and a GPS coordinate for a single house. But the synthesis goes even deeper. By correlating maps built from completely different phenomena, we can cross-check our most fundamental assumptions. Does the distribution of galaxy clusters seen in visible light perfectly match the distribution of mass inferred from weak gravitational lensing? If there is a discrepancy, it could point to new physics or a misunderstanding of how galaxies trace the underlying dark matter. Does the pattern of the cosmic microwave background align with the large-scale structure mapped by the 21-centimeter radio emission from hydrogen gas? Any subtle misalignment could reveal secrets about the universe's dark ages or the nature of dark energy. This holistic approach reduces the nagging uncertainties of cosmic variance and observational bias. It turns individual lines of evidence into a reinforced framework. A map drawn from light alone might have blind spots, regions obscured by cosmic dust or drowned in glare. A map inferred from gravitational waves alone might be sparse, highlighting only the most violent mergers, but when combined, they fill in each other's gaps, creating a composite image that is far more reliable and detailed than any single perspective could achieve. This is the future of mapping, a collaborative dialogue between every form of cosmic information. We are moving beyond a static three-dimensional model of positions and distances. We are building a dynamic multi-physics portrait of the cosmic web, one that shows not just where matter is, but how its different states, from dark and silent to luminous and magnetized, interact within the grand gravitational framework. It is a map that does not just depict structure, but reveals the ongoing conversation between all the forces and particles that make the universe what it is. The data from our cosmic census is a flood of unprecedented scale. Every night, the Vera C. Rubin Observatory's legacy survey of space and time will capture over 20 terabytes of raw images, a volume of information equivalent to streaming several million high-definition movies. Over a decade, this accumulates into hundreds of petabytes, a number so vast it defies everyday comparison. This is not merely a storage problem, it is a fundamental reimagining of how we do science. The photons collected by the telescope's giant mirror are just the beginning. The real challenge is transforming that ocean of raw light into a coherent, three-dimensional map of the cosmic web. This demands a new kind of astronomical infrastructure, one built on exascale supercomputers capable of performing a quintillion calculations per second and machine learning algorithms trained to see patterns no human eye could ever discern. The task is monumental, finding the subtle gravitational signature of a dark matter filament or the statistical whisper of a Baryon acoustic oscillation within a haystack of billions of galaxy positions, each point carrying its own measurement uncertainties and observational biases. Scientists write and refine immensely sophisticated codes, programs with names like Disperse and Nexus, which act as cosmic pattern recognition engines. These algorithms treat the distribution of galaxies not as a simple scatterplot, but as a topological landscape. They can identify the dense ridges that correspond to filaments, the vast basins that are cosmic voids, and the towering peaks of galaxy clusters, all by analyzing the connectivity and density of points in this billion-point data cloud. It is a mathematical form of cartography, drawing contour lines on the universe itself. To make sense of what they find, cosmologists constantly compare their observed maps to simulated ones. Projects like the Cosmos Sim database serve as public libraries of synthetic universes, where researchers can download the results of gigantic simulations and test their analysis tools against a cosmos where every parameter is known. This iterative process of mapping the real sky and refining the virtual ones is the engine of modern discovery. The silent, humming data centers and the lines of elegant code are the unsung heroes of this age. They remind us that the telescope is only the eye. The true vision comes from the brain, a global network of silicon and human ingenuity working in tandem. Mapping the cosmos has become as much a triumph of data engineering and computer science as it is of astronomy, pushing our analytical capabilities to their absolute limit to reveal the architecture hidden within the light. This map of everything compels us to ask what it is for. To chart the architecture of all visible existence is an act of staggering ambition, one that places our fragile, fleeting species in a relationship with the infinite. We are simultaneously humbled and exalted, reduced to a statistical whisper within a billion light-year filament, yet capable of comprehending the very structure that contains us. This cognitive reach, this ability to hold a model of the cosmos in our minds, is perhaps our most profound characteristic. It directly challenges any notion that the universe was made for us or revolves around our significance. We are not the center of this story. We are a recent, conscious expression of its unfolding processes, living on a speck of dust adrift in a web of unimaginable scale. This realization is not a cause for despair, but for a profound and grounding humility. It recontextualizes our conflicts, our triumphs, and our very existence within a narrative far grander than any we could invent. Some thinkers look to a distant horizon, wondering if this detailed atlas could one day serve a practical purpose for a civilization spanning millennia. Could the stable gravitational landmarks of superclusters and great walls become the fixed points on a future galactic navigation chart, a cosmic GPS for voyages between the stars? While such speculations belong to a future we can scarcely envision, they highlight that our fundamental drive to map our surroundings, whether a forest or the universe, is an intrinsic part of our survival and growth. This pursuit of pure cosmological knowledge is ethically intertwined with how we treat our immediate home. The same curiosity that compels us to point telescopes at the void also fuels our mission to understand Earth's climate, its ecosystems, and the delicate balance that sustains us. It is all part of a single impulse to see our context clearly. To know where we are in the deepest sense is the first step in deciding how to live. Ultimately, this grand cartographic project is not just about physics, it is about meaning. Mapping the cosmic web is a modern expression of an ancient human need to find our place in the story. It is a quest that blends relentless curiosity with deep humility, and in the face of such immensity, it cultivates a silent, enduring awe. We are the universe making a map of itself, and in that act, we find a connection that transcends our tiny coordinates in space and time. Our current map, for all its glory, is not the final word. There are frontiers in this cosmic cartography that lie just beyond the edge of our vision, territories we know must exist but cannot yet see in any detail. These are the unmapped regions of the web, the faintest threads and the earliest chapters, waiting for the next leap in our perception. The most elusive structures are the diffuse filaments themselves. While we can trace their outline through the galaxies strung along them and infer their dark matter through lensing, the wispy gas within the thinnest threads is often too faint to detect directly. This is the cosmic web in its most pristine, undisturbed state, a river of primordial hydrogen flowing through the darkness, and it remains largely invisible to our current arrays of radio telescopes. We hear its collective whisper, but we cannot yet make out its individual streams. Then there is the profound mystery of the cosmic dark ages, that epoch spanning from the release of the cosmic microwave background to the ignition of the first stars. For hundreds of millions of years, the universe was a vast, dark expanse of neutral hydrogen and dark matter, quietly settling into the gravitational wells that would become the first filaments. No stars shone, no quasars blazed. That entire formative period of web construction is currently a blank page in our atlas. We have the starting point from the ancient light and the later result from galaxy surveys, but the crucial middle act, the silent birth of the first structures, is hidden from view. Even within the brilliant hubs we can see, like galaxy clusters, there are unresolved puzzles. The physics is phenomenally complex. How does energy cascade through the superheated plasma in turbulent eddies larger than galaxies? How are particles accelerated to nearly the speed of light in the shock waves of cluster collisions? Our telescopes show us the glowing aftermath, but they lack the resolution to watch the storm itself unfold, to see the detailed mechanics of these cosmic power plants. These frontiers define the next century of exploration. To map the faintest gas, we will need radio telescopes of staggering sensitivity, like the full square kilometer array, with its thousands of dishes spanning continents, listening for the 21-centimeter whisper with unprecedented clarity. To pierce the dark ages, we may need to place ultra-sensitive radio telescopes on the far side of the moon, using our natural satellite as a shield against the radio noise of Earth civilization to catch the faintest signals from the universe's infancy. To dissect the turmoil within a cluster, we dream of instruments like an X-ray interferometer in space, a fleet of satellites working in precise harmony to achieve the angular resolution needed to see magnetic fields and particle flows in action. These unmapped zones are not failures, they are invitations. They remind us that every beautiful map we create is merely the most detailed version possible for our time. With each technological leap, new layers of the tapestry come into focus, revealing finer threads and earlier epochs. The unknown aspects of the web guarantee that the story is not over. Future discoveries in these faint signals and dark epochs could hold the key to understanding the true nature of dark matter or the precise character of inflation. The mission of the cosmic cartographer, therefore, is eternal. There will always be a fainter filament, an earlier time, a more complex dynamic waiting just beyond our current resolution, calling for a new generation to build a better lens and extend the map a little further into the darkness. The same branching pattern repeats itself across the universe, from the grandest scales to the most intimate. Look at a photograph of a distant cosmic filament, then glance at a scan of neurons in the human brain, or the delicate veins in a leaf, or the sprawling tributaries of a river delta. The visual echo is uncanny, a whisper of a universal language written in structure itself. This is no mere artistic coincidence. It is a profound clue that nature, when faced with the fundamental challenge of moving energy, matter, or information from one place to another under constraint, often converges on the same elegant solution, a connected, branching network. Scientists call this field of study network science, and it reveals that the cosmic web is not an isolated marvel, but one spectacular expression of a pattern woven throughout reality. The forces that shape these networks differ dramatically. In the cosmos, it is the relentless, patient pull of gravity acting on tiny quantum seeds over billions of years. In a tree, it is the flow of water and nutrients seeking the path of least resistance to every leaf. In our brain, it is the evolutionary pressure to wire billions of neurons for maximum efficiency with minimal biological cost. Yet, the resulting architecture shares deep mathematical similarities. They all balance the need for connectivity with the cost of building and maintaining links. They are all resilient, able to withstand damage to individual parts because the network itself provides multiple pathways. This universal pattern recognition offers a powerful two-way street for discovery. Algorithms originally crafted by cosmologists to identify faint filaments in galaxy surveys have found surprising new purpose. Researchers in neuroscience have adapted these very tools to trace the intricate wiring of the human connectome, mapping the brain's own cosmic web of neural pathways with stunning clarity. The cosmic cartographer's code becomes a neurologist's microscope. Conversely, understanding how information flows through a social network or how a fungal mycelium distributes resources can offer fresh metaphors and models for how galaxies might exchange streams of gas along dark matter threads, or how shockwaves of energy propagate through a cluster. This cross-pollination of ideas underscores a beautiful and humbling unity. The laws of physics expressed through mathematics give rise to familiar forms regardless of scale. The universe does not possess an infinite palette of blueprints. When efficiency and resilience are the goals, a branching, filamentary network often emerges as the optimal design. This realization transforms our map from a chart of distant objects into a page from a much larger textbook. The web connecting all galaxies is a close relative to the web of thought inside your own mind and to the web of life that sustains a forest. We are not just mapping the cosmos out there, we are deciphering a foundational principle of organization, a pattern that seems written into the fabric of existence itself, connecting the vast and the minute in a silent, structural harmony. This magnificent map is a story written in gravity and light. Our journey has revealed a cosmos of breathtaking order and complexity, a single, interconnected web that stretches from the quantum seeds of the Big Bang to the galactic metropolises shining today. We have seen how dark matter forms the invisible scaffold, a hidden skeleton upon which the luminous universe is draped. We have watched as galaxies, those brilliant points of light, trace its outline like beacons along a dark highway. From the patient, point-by-point surveys of early astronomers to the cosmic mirages of gravitational lensing and the digital universes born in supercomputers, we have assembled the tools to bring this grand architecture into focus. This is not a random scatter. It is a structured, evolving system where the largest architecture dictates the smallest destinies. The place of a galaxy within the web, whether on a quiet filament or in a violent cluster core, writes the story of its stars, its planets, and its potential. In this way, the cosmic web did not just build cities of galaxies. It set the stage for the slow, patient emergence of complexity and ultimately for life itself. Yet, with every new survey from observatories like Euclid and Vera Rubin, our map gains finer detail and in doing so reveals deeper mysteries. Each sharper image of a filament raises new questions about the nature of dark matter. Each precise measurement of a void's growth probes the relentless push of dark energy. The faintest statistical whispers in the data may yet reveal the mass of ghostly neutrinos or hint at physics beyond our current understanding. This map, therefore, is never finished. It is a living document of discovery, a testament to human curiosity reaching across the light years. Remember, this is more than a scientific achievement. It is the story of our origins. Every element in our bodies was forged in stars that could only ignite where the web's gravity gathered the gas. We are not just observers of this structure, we are its product, a conscious expression of its 14 billion-year evolution. To hold this map in your mind is to find your place in the grandest narrative of all. If this voyage through the cosmic web has reshaped how you see the night sky, share your thoughts in the comments below. For more journeys to the frontiers of space and mystery, subscribe and join us as we continue to explore. Keep looking up and never stop wondering about the magnificent, invisible web that connects us all.